welcome Muhammed Hammed. He is a PhD student at the University of Missouri, Columbia, and he is going to present on improving the quality of element level bridge inspections.
I'm Muhammed. I'm working with Dr. Glenn Washer, and I'm happy to present the result of two research projects that we completed recently for NCHRP and also for Missouri Department of Transportation to improve the quality of element level inspection. In order to get to the results of the two research, I would like to talk about the requirements, how we selected the bridges, and how we selected the inspectors, how we collected the data, and what is the status of quality of element level bridge inspection. The projects that we completed, one was NCHRP project 12104, improving the quality of element level bridge inspection. That part of that was the visual guide that's now available through the Manual for Bridge Element Inspection, second edition published by AASHTO, and another project was improving the reliability of visual inspection that we completed for MoDOT. The NCHRP project, we did some tests that in Indiana and Michigan, and now it's available online for download, but the Missouri project is not published yet. The NCHRP project goal was to improve the quality of element level inspection, and the objective was to improve the consistency of data collection and also describe or establish accuracy requirement for element level inspection. But for this presentation, the objective is to report the quality of element level inspection. This data that I'm presenting, it's not a representative for other states, but if you collect the data, the variability will be in the range that I'm presenting, but not precisely what I'm presenting here. The criteria, the inspection design that we did, it was for selection of the bridges. We did some tasks at Esprite Center, a steel bridge inspection training and engineering center at Purdue University, and how we selected the inspectors and how we collected the data. The bridges were control bridge model. Several inspectors inspected the same bridge at the same time under same environmental conditions, under same traffic control, and the bridges were ordinary size, 2 to 3 span, about 120 foot long. We selected the bridges to be common in material. We selected 2 pre-stressed bridges for Michigan and 2 steel bridges for Indiana. And these bridges had sufficient amount of defect in condition state 3. And the bridges were selected to not require traffic control. For NCHRP project, the criteria to select inspectors was strict. We had the inspectors to be team leader, have element level bridge inspection experience. We divided the teams into 2 groups, one as a control group and the other we provided the visual guide that I will show in the next slide for the group that we call it TGA. And TGB used the inspection forms that we provided, but they did just based on their normal practice. For MoDOT inspectors, we had 16 inspectors. They did just the bridges that we selected. They didn't use the visual guide. They used the inspection forms that provided for them. Here is for the TGA, we provided a visual guide. This visual guide had the condition state definitions for the elements that was to be inspected. We provided images similar to the definition of the condition states, and also the visual guide contained boundary images. It means that those images neither are condition state 2 nor condition state 3 similar, neither condition state 1 nor condition state 2. And the visual guide also contained a special estimate that is showing the inspectors how defects compared to the element dimension looks like, to assist them in quantification of the defects. For all inspectors, we provided an inspection form we prepared. It had the element, name and number, blank cells for recording the condition states, comment area, and we did not provide previous inspection reports for inspectors. We did several tasks at Esprite Center. Esprite Center is at Purdue University. It's the house for actual steel bridge elements decommissioned, and it is used for training purposes. During the earliest stage of the NCHRP project, we found out that the agencies are collecting data differently. Some agencies are collecting, quantifying each defect in order to get the total quantity of the element, while other agencies are like memorizing all the defects and then giving this as a percentage of the total quantity of the element. These agencies are doing tallying each defect, the others are doing as a percentage of total quantity. We also tested the quality of measurement for steel protective coating using area versus length. To do this, we mounted white appliques on the sides of two 77-foot-long steel girder bridges at Esprite Center. We did this because we are just concerned about the quantification, not the condition state assignment. And this white appliques actually convinced the inspectors to be consistent in quantification. What we found, as I said, we had TGA and TGB, but there was no difference between these two groups. But I kept the same format that we published the report. And here we have the vertical axis, the damage quantity, and the horizontal axis is the website number, tallying individual area. And here, similarly, it is percentage of total area. What we found was that when the inspectors are tallying individual defect to get the total quantity, they are mostly overestimating the inspection. But there is a good point that they are consistent. The variation is very small. Compared to when they inspect as a percentage of total quantity, the variation is big, and sometimes they overestimate, sometimes they underestimate. Tallying individual length, this result showed consistent with the tallying individual area. When the inspectors are tallying, they are mostly overestimating, but they are consistent. And when they are calculating based on the percentage of total quantity, the data are widely dispersed, and sometimes it's overestimated, sometimes it's underestimated. Now I'm going to talk about the inspection results that we collected from the bridges. Here is two bridges, a twine bridge that we selected for Indiana. But before talking statistically, let's see how inspectors are performing when they inspect a same bridge at the same time under everything is the same. Here is the open steel girder, which is inspected for corrosion. We see that for condition state 2, the variation is about from 0 to over 66% between the inspectors. And here we have condition state 3 similarly. This is the girder length, the vertical axis. This is the condition state. What we did, we combined condition state 2 plus condition state 3. This is actually damage. What if we sent like 14 inspectors at the same bridge site to inspect it? How is the variation of the report or the data collected by these inspectors? The variation is in the order of about 0 to 100%. Some inspectors see the same girder all good without any damage, while other inspectors are seeing the same girder fully damaged. This is the result for reinforced concrete bridge dig. We had 2 bridges in Indiana. This is I-1, I-2. This is total quantity of the element. This is condition states. We have one inspector that's very far away from the rest of the group. Similarly here, the dig area, we have the condition states. The variation is from about 0 to 50%. This is the wearing surface for Indiana inspection. The variation is seen to be from over 50% for condition state 2, condition state 3, similarly for the damage, regardless of the condition states. And this is for bridge I-2, the second bridge in Indiana. We selected the pre-stress bridges for Michigan. And here is the result for pre-stress girder inspected in Michigan. Here is the total length for the element. Here is the condition states, and here is the damage. The variation is, there is variation between the inspectors seeing the same bridge at the same time. And this is for the second bridge. Here is the bridge. This is a 3-span bridge. For Michigan, the bridge that I showed, it was with very high traffic volume. We selected 2 alternative bridges for doing the bridge dig. This is for bridge M3. This is the total quantity. The variation is very pronounced here. Similarly, the damage. And here we see that this is similar for bridge M4. Inspection exercise for Missouri project, we selected 2 steel bridges. One was a new bridge, the other was old, and one cast-in-place concrete bridge. Here is a sample data from reinforced concrete dig. It's the total quantity. Here is reinforced the total quantity. Here is the condition state. There is a variation here for condition state 3, and this is the damage. Similarly, for a steel girder, we see that there is a variation in condition state assignment and also the damage. Now let's translate all these inspector-based results into statistical terms. What does this variation means in terms of quality of element level inspection? Here is a select number of data from Indiana inspection result. We have reinforced concrete deck, wearing surface, open steel girder, steel protective coating. We have bridge 1, and we have bridge 2. The smallest coefficient of variation, which is a ratio of standard deviation over the mean, is at 55%. And the maximum is 142%. The rest is within this range. Similarly, for Michigan Department of Transportation, we have the reinforced concrete deck. We inspected columns using unit of feet to compare it with the current practice of unit of each. And we have the pre-stress girder. The smallest variation here is 19%, and the highest is 120%. And there is 2 zeros here. This 0 means that only one inspector reported a condition state in this, reported a quantity in this condition state. This is for Missouri Department of Transportation project. We have the reinforced concrete deck, the wearing surface, open steel girder, steel protective coating. The variation here is the smallest is 57%, and the highest is 184%. The conclusion from these 2 research is the element level data are dispersed. And the result is that the coefficient of variation is mostly over 50%, and sometimes it is over 100%. It means the variability is higher than the mean of the inspectors. The recommendations for NCHRP project was, in order to increase the quality of element level inspection, we need to provide the inspectors more trainings in order to understand the condition state definitions and also apply same procedures to collect the data to get consistent inspection reports. And also to do inspector calibration in order that all the inspectors within an agency to be on the same page of the procedures and practices, especially with the current edition of the element level inspection, using the visual guide to understand the definition of the condition states and also to apply a consistent method for collecting the data. If you enjoyed this presentation, you can search for the NCHRP 12104. This project is available for download now, and I will be happy to answer questions. Yes.
Did all the team leaders actually use the guide? Did you require them to use the visual guide?
Yes.
Okay.
Actually, we, for all inspectors, regardless of being in the control group or the one that used the visual guide, we provided a webinar 1 week ahead of the inspection exercise. And we provided the objective, how we would collect the data, how to use the visual guide, what is included in the visual guide, and we give them some time before going on the bridges to get familiar with the visual guide.
Did you happen to have the bias of the level of training of all the inspectors? Are they all the same, or one of beginner, one of professional? You know, that could be a big bias giving all this result.
We recorded the level of education for all inspectors, the level of experience, and also the strict requirement was to be a team leader. But we had some high school inspectors, we had some masters and some bachelors. Yeah. There was difference in their level of education.
Was there any talk of moving protective coating system to linear feet, or where we find huge variations where we choose consistency over more granular data?
Actually, when we did the test to see the quality of element level inspection, if we switch the coding from square feet to linear feet, but we could not find a defined trend to make a conclusion that one is superior than the other. But we did test the linear feet versus square feet for steel protective coating.
Did your study relate any of this to any existing or current NBI condition ratings?
We collected the NBI rating for the bridges that we collected the element level data. The NBI rating was more consistent than this, but then there is the issue that the variability within the NBI is from 0 to 9, but the variability in element level inspection is related to the quantity of the element, but not the condition number.
I guess I've always kind of thought, as much as I've done inspection, that the routine safety inspection is really just comparing that to an element level has always been the difficulty.
Are you saying that the consistency between the NBI and the element, or?
I think that's been a struggle ever since element levels came along. So
during another research project we completed, we found literature that when you transcribe element level inspection to NBI rating or vice versa, the correlation is not good. This is why we did not compare the element level inspection data with the NBI rating. Statistically, this issue is that the NBI rating is qualitative and element level inspection is quantitative. This is two different scenarios. Thank you.
Okay, all right, thank you very much.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.